Good afternoon, everyone. Thank you for joining us here in Washington, D.C., and to our virtual audience online. We appreciate you being here as well. Next up, we are glad to welcome you to a presentation from our WEDI organizational member, Edifex. Niraj Katwala, the VP of Core Technology, will be presenting the session From Thin Air to Precision Data, the Power of Generative AI in Electronic Data Interchange and Medical Records. Core Technology focuses on many things to include machine learning, AI, and natural language processing. So have quite a bit to learn. Niraj, the floor is all yours, sir.
Hey. Thank you, Bill. Hey guys, hi. So we're going to start with a very simple, clean definition of AI and what are the subsets of AI, and then move into like what brought us here in 2023. What was the big reason why there was this mega, I think, something really dramatic happened in 2023 where everybody's talking about AI, which was not the case. AI is not new, but suddenly in 2023, it became big. So what happened? And then from there, we will jump into AI for healthcare. And then from there, we will go into AI as it applies to what is it that a specific use case that we are working on at Edifex. So that's going to be the flow. General AI, healthcare specific AI, what are we doing at Edifex? And then a very specific use case within what we are doing at Edifex. So I have this diagram which I prepared specifically for this presentation. There's a lot of confusion as to what AI is. So AI is building a system which kind of learns by itself, okay? It learns as it gets used. So the more you use that system, the more data you feed into that system, the smarter that system becomes. That is effectively a system which is AI enabled. Within the world of AI, there is something called AI algorithms. So there are three big types of algorithms or major types of algorithms which exist. The first one is what I call regression algorithms. So these are algorithms which are used for predicting some kind of a price, okay? So think about predicting the price of a house or predicting the price of a stock in the financial world, or more specific within the world of healthcare, if you want to predict what is going to be the cost for a treatment or a procedure or a lab or treating a condition as you move forward with that patient, right? So that is what are known as regression algorithms, okay? Where your data itself, when it comes in, is already in numerical form. And all you're trying to do is to come up with a future prediction of some kind of a price for a use case. The second type of algorithms are called classification algorithms. So here you are classifying the data that you have into different segments. A very simple example is spam or ham email. A good email or something which is a spam email. That's a very simple example of a classification algorithm. Or in case of healthcare, it is like, which is the ICD-10 code which applies to this piece of data? Is it a diabetes-related code? Is it a hypertension-related code? So provided you have data from a particular patient, what is the ICD-10 code that you would classify for that data? That would be a classification algorithm. Okay, now the third and the most interesting thing or most interesting set of algorithms are something which were always there, but really took shape over the last 12 months. And that had to do with obviously the introduction of ChatGPT and all. They came to the fore. They were always existing, but they came to the fore with ChatGPT, and they are known as large language models or generative AI models. And what they are doing is they are doing very specific things with natural language. For example, language translation is a use case in generative AI models, or generating a summary for an article, or writing Java code. Each one of these use cases, you are generating new text, okay? That's why they are known as effectively known as generative AI models. Okay, and there are a few other definitions which I want people to be familiar with. Natural language processing is an adjacent technology to AI. It's not. It's kind of it's not the same as AI. Is more important. NLP. You use NLP to go through text and understand that text. That is what the purpose of NLP is. You can apply AI to improve your NLP, but they are kind of different. And then within the world of machine learning or AI, there is machine learning. Machine learning is the process where you are actually training that algorithm with a set of data. Okay? Historical data is what you use to train your model to predict future stuff. Okay? So that's the process of machine learning. And within the world of machine learning, there are two items or two definitions which are good to know. One is features and another one is labels. Features are things which are inside the data or elements of the data which are more which are used to predict future prices. So let's take a very simple example in case of predicting the price of a house. So maybe the number of bedrooms or the number of bathrooms or the size of the lot or the square footage of the lot. These are all features which are applicable for predicting the price of a house, right? So that's a feature. In case of healthcare, if you're trying to predict the cost of treatment, maybe the duration of the treatment, maybe the condition that you are treating. Those become the features, okay? So that is what a feature is. Now, in order to train your model, you need to know what is the right value which is associated with each training data element, right? So for example, if you want to build an algorithm which is going to classify an email between a spam email and a non-spam email, the training data has to include a set of emails where you already know what is a spam email. So that is a label. So for an email, if you know that this is a spam email, then the fact that it is a spam is a label. Okay. So I hope this is basic like AI one-on-one, but for us to go deeper into the discussion, I just wanted to clear the definition of these terms so that we can all talk the same language, at least for the next 45 minutes or so. Okay. Now let's move to this. So this is a very important slide, which I think there's a lot of talk going around. Okay, hey, is AI for real? Like, is this all hype? Right? There's this. How can a $1 trillion company be born out of this? Or like, how can people say this is a $7 trillion market or whatever numbers people are dreaming up nowadays? So in my humble opinion, this is not hype. This is something which built up over the years. It's like, something which nobody was seeing it, but it was like a volcano which was seething and then finally it erupted. It's literally something like that which happened. And I'll tell you why, because companies like Google, Meta, OpenAI, they were always working on some groundbreaking stuff for several years. So it's not like they were, say, Tesla is another one, right? So they were already doing a lot of AI work. But there are three things which happened over the last few years which truly made 2023 the year of AI. So I will just go through those three things very quickly. So first thing, in the mid-2000s, right? So let's say around 2007, 2008, I don't know the precise year, but there was this guy, Jensen Huang, he's the CEO of NVIDIA, okay? So he has this nice company, NVIDIA, which he has had for 10 plus years, and it is doing well. He has built a chip for graphical processing, right? So basically here is a screen, and I want to show a picture on that screen. So I have a file, which is a JPEG file, which is sitting on disk, and I want to show the picture which is in that file on the screen. So he built a chip for that. He called it a GPU, graphical processing unit, okay? And he was selling them and he was happy, everybody was happy, it was doing well. Well, come 2007, 2008, he's in some meetings with some folks in Silicon Valley, and they're all talking about how difficult it is for them, that they have these beautiful algorithms that they have written in machine learning and AI, but they don't have the horsepower or they don't have the machine speed to process all this data and really make their algorithms work. So he spoke with them and he's like, okay, what type of algorithms are these? What is it that they are doing internally? And he understood that it was all linear algebra, matrix multiplication, those kind of things, okay? Mathematical stuff. Then he's like, okay, but this is what my GPU is doing. And I've been doing it for 10 plus years, but I've been using it for processing images and showing them on a screen. He realized that the algorithms were almost identical for machine learning. Okay, which he has already built a chip. It takes 10 plus years to build a chip. Now he finds himself with a chip which he's using for graphic, which he can use for machine learning. So he completely pivoted his company to machine learning. Okay, he kept doing his graphical processing work, but he completely pivoted his company and basically started focusing on building out chips, GPU chips for the machine learning market. So that was a very mega event which happened. And suddenly the speed at which data could be processed in the ML world, literally in certain instances, it was 100,000 times faster. It was that good. So this was like literally an apple fell on his head, if you can call it. But it was the second instance in history where something like this happened, okay? And now today, if you look at you all know NVIDIA price, it's a $1 trillion company because of this. His pivoting his company from being a GPU, graphical process for machine learning purposes. So that's what happened. Well, the second thing which happened, so that's the hardware part. We got the hardware right. Now, there was this team of research scientists in Google. They called them, that group was known as Google Brain. And their job was to go around writing papers, doing all kinds of research, and they wrote a paper. That paper was called Attention is All You Need, okay? And it had to do, it was a specific type of an algorithm. What it was very good at was taking any type of text, which anybody had, converting that text and each word in that text into a numerical representation, like a series of numbers. So text gets converted to numbers, okay? And that part of that, it was called a transformer. The word used for this algorithm is called a transformer. It had two parts, an encoder and a decoder. And the first part was converting text to numbers and then doing some processing on those numbers and generating text out of the resulting numbers, okay? So text to numbers, numbers to text, okay? So that was a transformer, the encoder-decoder technology that was born. And people built models on it and all. Google built models, Facebook built models. And there was this company, Elon Musk and Sam Altman, two guys, complete geniuses, absolute geniuses, they had started called OpenAI, okay? And OpenAI, and then Elon Musk got bored. He had Tesla to run. He had $300 billion. It's like, I have had enough of this. I'm going to go and do something else. And he gave the whole company to Sam Altman. Sam Altman kept working like crazy with his team. And come November 2022, he launches ChatGPT. So what is ChatGPT? ChatGPT completely disrupted what I call the search marketplace. Okay? Search is the number one software application in the world today. If the amount of money which is generated, the amount of people who use that application, search is the number one application. So now, suddenly, everybody in the world is talking about ChatGPT, and they are talking about AI and all, and now because of NVIDIA, because of the transformer technology, because of people, so many people, like 10 million people signed up for it within, sorry? Oh, okay. Yeah. Oh, okay. So anyway, I just wanted to give you some context as to what happened and why AI has become so big. Okay, so that is the reason. Okay, because this person, Sam Altman and his team at OpenAI, with the support of Microsoft, built something which, for the first time, threatened the complete monopoly that Google had. Okay, in that space. Okay, so now that's the general world of AI. Now let's focus on healthcare. Okay, so what happens in the world of healthcare? Okay, so in healthcare, there is structured data and there is unstructured data. Structured data comes from EMR tables or it comes from claims systems, and unstructured data comes from patient charts, medical articles, policy bulletins. You guys know this better than anybody over here. But if you look at the list of unstructured text data, that is where all the unstructured text data is, and then EMR and claim system is where most of the structured data is. And if you look at the left-hand side, those are the use cases where the structured and unstructured data is used. Risk adjustment coding is one use case, prior authorization, quality metrics, clinical trials recruitment. Everywhere you use this data to go, which is mostly patient data, which you're using to go and do something, right? Like in case of risk adjustment, you're trying to figure out what are the correct ICD-10 codes which are associated with a chart. In case of prior authorization, you are trying to figure out whether a particular treatment is approved for or should be approved for request coming in from a physician. Quality metrics is like how good is this physician treating his patient, so on and so forth, right? So now, these use cases always existed. Okay, I'm trying to cover the 90% of the. There were use cases which AI brought forth which were never there, but a majority of the use cases which I'm listing over there, they were always there. Okay, it wasn't like these use cases were born out of AI. They were always existing. Well, what did AI do for this use cases is what I want to focus on. Okay, so and we are going to focus on one specific one, which is the risk adjustment coding use case. We can focus on any one, but that's the one which we are going to talk about today. Okay, so how was this all working before AI is an important thing to understand. So it's not like we weren't doing risk adjustment before AI came along, right? But that was mostly done using a taxonomy. A taxonomy is basically a list of terms, and NLP. NLP is natural language processing, which would basically go through a chart, word by word, understand that word, okay? And based on that word, say, hey, this person has this condition, and hence if he has this condition, this is the ICD-10 code, which he should be assigned. That is how it was working in the past, okay? Got it? There was no AI involved. Okay. Now, what is NLP? So let's just very quickly look at this diagram, which explains NLP. There is a patient chart which comes in. That patient chart gets broken down into basically documents. Okay? The way a patient chart is constructed is a collection of documents associated for that patient in one big PDF. Think of it that way, right? So when that chart comes in for processing, okay, in the risk adjustment or in the quality world or for clinical trials recruitment, doesn't matter, right? It gets broken down into documents. Documents get broken down into sections within the document. Sections get broken down into sentences or paragraphs. Then sentences get broken down into words, and then you go and find, is this word a condition? Is this a treatment? Is this a lab? Is this a medication? What is it, right? If it's a medication, is there dosage information associated with this medication? If it's a lab, is there lab values associated with this lab? That process of identifying the information within that chart is effectively NLP, okay, or entity extraction based NLP. I hope that's clear to everybody. And there are a bunch of knowledge bases which are associated with it. You do things like stemming and correction, and there are code translations from one code set to another code set. There are, identifying dates, because dates come in all different formats. So how do you identify a date, right? Negation, right? Does not have diabetes versus has diabetes, right? This is how the NLP world worked, okay? And this was what was there before AI. And this is still there, but I just wanted to point out that this is how it worked. And to make NLP work, if there is a chart and there is a word inside the chart, and you want to know which of these words are conditions, which of these words are medications, right? So you need some kind of a dictionary. That dictionary is going to say, hey, this is the set of words which indicate a condition. This is a set of words which indicate a treatment, medication, so on and so forth, right? So that is a taxonomy or a dictionary, okay? The difference between a taxonomy and a dictionary is basically one-to-one. Okay, this is a word and this is the meaning of that word, right? That's effectively a synonym. A taxonomy is more complicated. It has related terms. It has codes which are associated with it, so on and so forth, okay? So combined, the NLP and the taxonomy is what was used prior to AI for coming up with reasonable, correct, implementations of the different use cases that I was talking about, whether it be risk adjustment, whether it be clinical trials recruitment, whether it be quality, whether it be whatever, right? So those are prior authorization, et cetera, okay? So now, here is a, within the world of Edifex, these are the things which we are using now. Now we have started using AI, right? A few years back. So what is it that we are using it for? Risk adjustment is one, value-based payments, prior authorization. So those are three things which we are using AI for. Okay. In my first slide, which I showed you regression algorithms, where we are predicting the price of well, that is all numbers from the beginning. There is no text. Okay, so the value-based payments, which is the second one over here, over there, we are only using regression algorithm. There is no LLM used because it makes no sense to use an LLM. LLM is large language model. A large language model has to do with language. There is no language when you're dealing with numbers. So over there, we are using AI, but only for specific, numerical information. Whereas in case of risk adjustment and prior authorization, we are actually doing a lot of processing of text. That's the difference. And that is where LLMs make sense, okay? Is this making sense? Any questions from anybody? Okay, cool, I'll continue. Okay, now, the biggest thing which happened with AI is typically there would be a production infrastructure, okay? That production infrastructure would be a set of machines which are used for a specific use case, correct? There is hardware which you have deployed. And for example, there is hardware which is used for, okay, hey, I want to predict the ICD-10 codes out of this chart. So there is hardware for that, right? Well, with the when you want to enable a use case with AI, the first thing you need to do is to build a training infrastructure in your organization, okay? Which is a new thing which was not there before. So previously, there is a set of machines, you would input a chart, out there would be like, it would do the NLP processing and it will say, hey, this is the code which is associated with it. Okay, well, with AI, what's the difference? Well, you don't just have one chart. You are effectively collecting all your charts you have ever processed in a data warehouse. Please understand, this is a very fundamental difference. Previously, there would be one chart which you would process and say, hey, this is the ICD-10 code, you're done, right? Now with AI, what you do is you take every single chart which you have ever received in history, right, through your company's history, right? And this is it could be claims data, it could be clinical trials data, it could be anything. I'm just saying this is what you do, where you build an infrastructure where you're collecting all the historical charts in one place, and for each one of those charts, you are going to have an associated correct ICD-10 code from the beginning. Okay, that's known as a label, the correct ICD-10 code. So now you have a set of charts and you have a set of labels which are associated with it. Now, What you are going to do is you're going to take all that data and you're going to take some machine learning models and train those models using that data. Okay? So in our case, we are using 3 different models for training this data. Okay? There is, we are first taking all the sentences which contained an important term which indicated a condition. We are taking all the concepts which are associated with a condition, and we are also taking the entire chart text. All 3 things we are taking, and we are building 3 models which are associated with it. Okay? This is the process, this is called the training process, okay, in case of AI. This does not exist in case of system which is not AI enabled. I just wanted to, okay, so that is the big thing. This is expensive. This was the reason in the past, before NVIDIA came up with their GPU processing power, right? This was very expensive to do. So a majority of the world's use cases would not work because either they did not have data, and if they had data, they didn't have the horsepower or the machines to process that data. One way or the other, they could not do the work, okay? So now, because we have this relatively cheaper infrastructure, right, we are able to do this. About 6 years ago, when we started working on risk adjustment, the other problem, so one was the hardware. The other problem is data. So in healthcare, right, we are all in healthcare, so it's good to discuss this for a minute. The most difficult thing is what a doctor does, okay, as a human, right, which is examine a patient and say, this patient has this condition, right? And then he has this condition, and this is how we are going to treat him. You solve those 2 things, basically you don't need doctors, right? Like that is, unfortunately, it is an extremely complicated thing. And that thing is used, that capability of being able to look at the data of a patient and figure out what is the condition that he's suffering from, to the right to the most granular ICD-10 code, because there are 80,000 ICD-10 codes, okay? To come up with the right one ICD-10 code or 2 ICD-10 codes which are associated with that patient is an extremely complicated thing. And that nut has not been cracked. Everybody keeps talking about, yeah, I generated Java code, and I generated this, and I generated this, and I wrote a poem, and I basically are using ChatGPT. But the most difficult, why don't you solve cancer? So somebody asked this question, hey, if ChatGPT, why don't we get ChatGPT to solve cancer? Well, it turns out it's an extremely difficult thing to do, okay? So that is what everybody, in one shape or another, everybody's trying to solve that problem, okay? How do we go and figure out, based on the data for a patient, what is the condition he has and how are we going to treat him, right? If we can do that, then a lot of stuff becomes very, very easy in this world. But to get to that granularity, to that, and why is that? Because there are 80,000 ICD-10 codes. 80,000 ICD-10 codes, meaning that for me to predict an ICD-10 code, I need training data for each one of those ICD-10 codes. Otherwise, how am I going to do any AI? There is no AI without training data. So now, for me to collect, or any organization, even the United Healthcare, or which is probably the largest healthcare organization in the world, to collect that much data for patients at 80,000 code level is an extremely difficult thing, okay? So most systems which exist today are a hybrid of the traditional approaches of finding the codes and the new AI approaches, okay? So what does that mean? If it's a very common code, like E11.9 is diabetes, okay? I10 is hypertension, okay? Well, 40% of the people in the world have hypertension or something ridiculous like that. So you are able to find charts and patients who have hypertension. So there is enough training data for that, okay? Same thing with diabetes. You will find enough training data for that. But if you go into the more esoteric diseases, diseases which are very, very uncommon, or very, very specific forms of diabetes, right? Diabetes with CKD, et cetera, or something more complex, like 3, 4 diseases combined, right? It becomes very difficult to find that training data, okay? So most of the systems which exist today are traditional systems which are built using pure natural language processing, and in addition to that, there is systems which are basically NLP plus AI systems. Okay, so whenever you have a lot of training data, you use AI. Whenever you don't have training data, you use the traditional systems. Okay, so anyway, we take all the training data, we train these models, and then we move those models into production. Okay, so then when it is in production, it is called inferencing. Okay, so something like this happens. So if you read through this, it's not that difficult to understand. Typically when a physician sees a patient, there is a code which the physician assigns to that patient. Okay, you have this condition, right? Now, when NLP runs on the patient chart, it probably finds some additional codes because the physician has missed some codes, right? Which he should have, because physicians are little bit like, they are busy people, so sometimes they forget some codes. So then we find the Y codes. What ML started doing, at least for us, is it started finding codes beyond what the physician and natural language processing was finding. Okay, so that is the Z codes. In addition to that, what it did was it gave a higher confidence to a certain set of codes. So now the number of codes, correct codes associated with the patient data increased, and the confidence of the system and everybody in general of whether these codes are correct or not increased with AI. Okay, so that is the power of AI, and this is true for every single use case. Okay, what happens is not only is it's effectively enhancing every use case which is out there. Okay, it is adding more correct information for every single use case. Okay, that is what AI is doing. Okay, can we switch now?
Sure.
I'm going to do a very quick 5-minute demo, which will probably get you a little bit more in.
Can we start from this point, or do you want us to back out of this?
No, this is good.
Okay.
No, actually,
Bear with me.
is this what is this? No, go back.
Okay. Bear with me just a moment.
Okay, this is the slide, yeah, in screens.
Hang on 1 second. And then
Okay,
bear with us just a moment.
yeah. Good.
That's it? All right.
It's not.
Bear with me just a moment here.
It worked here, but it's not showing over there.
Okay.
Mirroring your screen, or not mirroring your screen. Yeah.
You know what? Let's just forget it. I have screenshots. We'll just go through the screenshots.
Yikes.
Tell you what, if we can't get it in, let's say 15, 20 seconds, then we'll
Okay,
get that option.
So,
Oh, you can't see it on that screen, though.
it's okay. I'll just, yeah. You know what? Let's
Will that
just,
allow you to-
can we go back to the original computer? I have slides over there, which we are just going to use.
You just want the slides back up there?
Yeah, just the original slide deck. Oh, okay, I got it. So, I got. Okay, so here is a very simple demo which I'm going to just walk through because it's easier with the slides given this. So here is a note. So a physician has just seen a patient, okay, and he has written down this note. Okay, that's what this is. And what we want NLP to do is to go through this note automatically, and like here is the process. The input is, the chart, right? It goes through entity recognition, meaning that it extracts the sentences, the concepts, the chart text, all of that. And basically those things get fed into the models, okay? And then based on the models, you collect all the different codes which are associated with that patient, right? And that's the final result, okay? So,
Forgive me to rush.
yeah. So what NLP first does is it goes and finds all the codes which are associated with that patient by going through the chart information, okay? And the list of codes which are on the left-hand side are what NLP found. There is no AI involved at this point. All that happened is that the data went in and the chart went in and NLP identified these codes. Now, the next step is, right, we go and run those 3 AI models, okay, which have been pre-trained using all the training data. And we find additional codes. Each one of those 3 models, the concept model, the sentence model, you just have to bear with me, these are models which AI builds, right? And those generate additional codes, okay? So now we have additional codes which are generated. And then finally, okay, in the last step, it's called ensemble learning. All the codes which are generated by NLP plus all the codes which are generated by AI, right, or the machine learning, the 3 models are combined into one, and a new confidence score is associated with each one of those codes, okay? So in the world of risk adjustment, it is very, very critical when you're submitting codes to CMS, you want the codes to be accurate and you want the codes to be complete. You cannot, if you do not submit a code, you don't get paid for it. Okay, so it's not a way of overcoding or anything like that. You're just trying to get the right codes. So that's the process. You first run it through NLP, you then run it through machine learning, you collect the codes, you sort them, if there are duplicates, you sort them, find the correct set of codes, and that's what gets submitted to CMS. Okay? So that is effectively my entire presentation. I hope I conveyed the power of AI. It is a little bit amorphous. it's difficult to like just visualize everything, but at the end of the day, there is a bunch of algorithms. Those algorithms are trained with training data. Then those, what you produce are known as models. Those models get put into production. When a new chart comes in, okay, you run that chart through those models, predict codes, and those codes get submitted to CMS. That's what happens. I'll just run through a couple of other use cases. Similar to this use case, which is related to risk adjustment, there are other use cases which have to do, say, only with claims data. One such use case is looking at all the training data which is associated for, let's say, a treatment like TKR, a total knee replacement, right? And, basically doing just numerical analysis on it and figuring out what is the, right price for this procedure in a particular zip code or national average or, on a per physician basis, so on and so forth. Okay. Thanks, guys. So that's basically it. Questions? Yeah.
I've got one. I know that we're doing this sort of human in the loop
Mhm.
AI, right?
Yeah.
We're serving those potential conditions up to a clinically aware coding specialist. How far away are we from generating something that will have less human interaction?
So different use cases have different fidelity or accuracy. Typically, in the world of risk adjustment, a coder who is actually assigning the codes manually, that is how a lot of work is done today, is about 85 to 90% accurate. And I have already I've taken different sets of coders and given them the same charts and seeing how common the codes are which are generated by each one of them. And it's about 85% accurate. So they are at about 85%. Today, without machine learning, we were at about 60%. With machine learning, we have scooched it up to about 70%. So we have about 15-20% to go. So if we can get another 15 to 20% more accurate, we are neck and neck with humans. Okay, so that's where we are today. Each additional percentage, like as you go up, higher up, it's more and more difficult. Our challenge is not with the more common codes. There is a lot of data, training data associated and available for the more common codes. Our challenge has to do with the less common codes, which are esoteric, but also those codes have more dollar value associated with it. So trying to get to the training data for those codes is where the challenge lies.
I guess along those lines, like if older charts or however they used to do it was only 70 to 80% accurate, where do you get accurate training data? Like how do you know that was the right answer to the
Yes, yeah, right. Yeah, it's a challenge. It's a problem, but I don't have a good answer for you. But we have to use what we have, right? So, it's a problem. I don't know what she's asking. It's an important thing, right? Because I said if humans are 85% accurate, right? And that is my training data. How can I ever go beyond 85% is what she's asking. So, sorry. Yeah, go ahead.
So when you start to apply that
Mm-hmm.
real words and all this, right, it's a probability issue, so you're going to have some codes which were assigned by error, so wrongness. So do you have some processes in place to feed them back to the system?
Yes. Yeah. So the way it works is we run NLP. The results of an AI, the results of the codes which I was showing, right? These codes now go today in our process today. They go to a live coder, a human. He then looks at it and validates them. and agrees or disagrees with some of them, basically, right? That becomes the labeled training data, right? So every month we get about 15 to 20,000 charts. Oh, sorry, 100,000, 100,000 to 150,000 charts. They all get coded by, they all go through the NLP AI process, then they get coded by the coders, right? The result of their coding exercise again gets fed in as training data. So every month, the amount of training data is increasing. And that is the definition of a machine learning system, where as the system gets used more, the amount of training data increases, the precision of the system increases.
We have an online question.
Sure.
Do you have to have a coder review all the AI NLP generated codes before submission to ensure the accuracy?
Today, yes. Until we reach the 85-90% threshold, we cannot take the risk. Because the way, I don't know if, just to say, the HCC world, the way it works is if you over submit. So let's say NLP and AI predicts a code which should not be associated with that chart, right? If CMS does something called an RADV audit, and if they in that audit they find that, right, you get fined, but you don't get fined for that chart. They extrapolate it to the entire population. So very dangerous. So that is the reason, until we are confident, and it is going to take some time, and we can get to that threshold where we are above the 85-90% mark, where we know that we are better than the human coders, we have to get them reviewed by the.
Well, thank you very much. That wraps up all of the time that we have before our lunch break, but I'm sure you can find all of our fantastic presenters during the, networking break. We're going to have snacks. Just in case anybody's still hungry, we're going to have snacks. And then we'll be back in here the next session, and here will be payer and provider considerations on new solutions for prior authorization, finding common ground.
Thanks, guys.